Modern language models are transitioning toward test time scaling. They must navigate complex decision trees and process extended trajectories entirely at inference time. Softmax attention carries a structural disadvantage, quadratic time complexity, and a linearly growing key value cache. To map an ongoing interaction, the architecture must store an ever-expanding history of tokens in memory. Every new step demands more physical space. Eventually, this expanding cache hits the physical limits of GPU memory, halting the entire system. This memory overhead creates a computational wall, making test time scaling unsustainable on current hardware. Kimi Linear is a hybrid architecture designed to eliminate this inference bottleneck at the architectural level. The defining metric for autonomous agents is time per output token, or TPOT. This latency measurement dictates whether a model can process information and respond within real-world time constraints. This chart tracks time per output token, scaling up to 1 million tokens. The softmax baseline curves sharply upward. In contrast, Kimi Linear maintains a flat, low-latency trajectory, yielding a 6.3 times decoding acceleration over the baseline. This acceleration is achieved through two concurrent structural choices: a 3-1 macro-level hybrid routing strategy, combined with a specialized micro-level linear kernel. This speedup results from a refinement of the gated delta rule itself, addressing finite state capacity limits by providing more precise control over memory decay. The system design begins at the physical macro architecture of the neural network. Pure linear architectures typically struggle with long context retrieval. To maintain high-fidelity recall, the network requires a subset of global attention layers to preserve long-range information flow. This diagram outlines Kimi Linear's specific routing ratio. The architecture interleaves 3 Kimi delta attention layers, or KDA, for every one multi-head latent attention layer. By reducing global attention operations by 75%, the system shrinks its total KV cache footprint by an equivalent margin. Within this hybrid structure, Kimi Linear applies no position encoding, or NOP, to the global MLA layers. Instead, the KDA layers act as a data-dependent multiplicative positional encoding, taking over all sequence order tracking duties for the model. These linear layers handle sequence order entirely, allowing global layers to operate without positional overhead. At the micro level, the KDA module addresses the primary failure point of linear models, the inability to perform exact copying tasks. Linear attention uses a fixed-size memory state. Without precise forgetting mechanisms, incoming data overwrites crucial older information. Standard approaches apply a single scalar forget gate to an entire attention head, acting like a master volume dial that dims every data channel simultaneously. KDA introduces a channel-wise diagonal gate, granting each feature dimension an independent forgetting rate. This granularity allows the model to preserve specific crucial memories while discarding noise at a subhead level. This architectural choice allows Kimi Linear to pass synthetic exact copying tests, like the palindrome and association recall tasks, that often defeat purely linear models. By controlling the forgetting mechanism down to the channel level, KDA matches softmax level recall perfectly. Theoretical memory efficiency has zero practical utility if it cannot execute efficiently on modern hardware accelerators. To utilize tensor cores, recurrent state updates must be mathematically compressed into parallel, chunkwise operations. The diagonal plus low rank, or DPLR, structure is an expressive way to map these state transitions, but it is historically associated with high hardware latency. This flowchart illustrates the general DPLR pipeline. Calculating fine-grained decay requires secondary chunking steps, which introduce computational overhead and additional matrix multiplications. KDA introduces a mathematical constraint to this formulation by binding specific variables directly to the input keys. This variable binding eliminates the need for secondary chunking, removing 3 distinct matrix multiplications from the computation path. This chart plots sequence length against execution time. By removing the secondary chunking steps, the KDA kernel executes nearly twice as fast as the general DPLR formulation. Despite bypassing these computational bottlenecks, KDA remains mathematically consistent with the classical delta rule. KDA implements the expressivity of DPLR while eliminating its historical hardware latency. The ultimate test for any new attention architecture is its raw capacity for long-form reasoning under reinforcement learning. We evaluate this by comparing Kimi Linear against full attention baselines on reasoning-intensive mathematics tests. This graph tracks RL training accuracy on the Math 500 benchmark. The standard full attention baseline establishes a clear curve of rising accuracy. Operating from the exact same start, Kimi Linear reaches a higher terminal accuracy with a steeper trajectory, demonstrating superior sample efficiency. This performance advantage extends to long context benchmarks like Ruler and Repo QA. The hybrid design preserves global information flow, while the efficient linear layers process the local context. Kimi Linear established a higher performance ceiling than the uncompressed softmax baseline in these reasoning tests. A 75% reduction in K3 cache footprint yields a 6.3 times decoding speedup at a 1 million token context. This performance is the direct result of channel-wise fine-grained gating and hardware-optimized DPLR chunking. Historically, hybrid models were viewed as a structural compromise, reducing model quality to save computational overhead. Kimi Linear establishes that hybrid designs can surpass the accuracy of uncompressed global attention while maintaining sub-quadratic efficiency. By isolating positional inductive biases and optimizing the state transition math, hybrid architectures have reached a new level of maturity. By resolving the capacity limits of linear attention, Kimi Linear provides the high-throughput, low-memory foundation required for long-horizon, decoding-heavy AI agents.